So should I start now?
Yes, you can start.
Okay. Right. Hi, everyone. I'm Seungbae Kim. Thank you for joining our tutorial, Fairness in Computer Vision, Datasets, Algorithms, and Implications. This tutorial is organized by Angelina and myself, and Professor Olga and Professor Jungseock. And we are very excited to have this tutorial on fairness in computer vision. This tutorial introduces the recent ideas in computer vision fairness and shares some pointers to recent literatures. And our target audiences are the researchers and practitioners who want to use the computer vision tools even without having the technical background. And the advances in computer vision increase the utility in a wide variety of applications. For example, the object detection is used in driving automation by recognizing nearby cars or pedestrians. And face recognition is used to detect and analyze face attributes, emotions, or even personalities. And in addition, image captioning is used to explain the images by generating text descriptions based on detecting the object and understanding the relationship between the objects. As computer vision technologies are used in such tasks, it is imperative to consider fairness in computer vision. As computer vision technologies, the computer vision community has taken the fairness concerns very seriously. And in recent literatures, there has been an increasing amount of work on quantifying and measuring the fairness and bias measurement and mitigation, accuracy gap reduction, and developing new resources for improving fairness in computer vision models and datasets. This tutorial has two main parts. The first part will focus on understanding biases in computer vision. I will cover where the computer vision biases originate from and what their impacts are on our society. Then I will review three types of biases and mitigation strategies widely used in computer vision with key reference papers. In the second part, Angelina will present how to apply computer vision with fairness consideration with a running example. Before we start, let's take an automated recruitment as an example of a practical application that uses the computer vision models. With the advancement of machine learning technology, more and more companies are applying the automated techniques to their hiring process. The automated models can analyze and evaluate the applicants' resumes and match them to the right department, or generate the interview questions to evaluate the applicant's abilities, or having help the scheduling throughout the recruitment process to hire more suitable candidates. And this automated video interview can be an example of a practical computer vision application. So this application is used to assess candidates' soft skills, motivation, proficiency, and expertise by using face recognition. And these automated tools might help companies to objectively evaluate the candidates. However, what happens if the pre-trained computer vision model that is used in this application is biased? What if the pre-trained model favors males over females because of a skewed training dataset? If the model is biased, then the automated interview tool may produce an incorrect assessment or unfair treatment across different genders or race groups. This can be a bigger social problem, such as discrimination against a particular gender or race. Then, where do these biases come from? Bias can be created in many different places, but we can consider it from two different perspectives: social bias and media bias. Social bias is the result of stereotypes or psychological cognitive bias commonly held by individuals or societies. a recent study shows that there is a clear difference in people's perceived emotions according to the gender. For example, the people tend to perceive female faces as happier than male faces. If people with these stereotypes label the dataset, they will create a biased dataset. And media also plays a big role in creating the visual bias. There are many reasons, but depending on the media, it is possible to provide biased images only to a certain groups. The conservative media, for example, can often offer the good-looking pictures of the conservative politicians. In addition, the images containing a specific group may have distinct characteristics compared to the other groups. For example, the photos related to sports may have more males than females. And a recent study found that images of conservative politicians can contain more objects such as the flags or uniforms, but images of liberal politicians project an image of care for the community. This data bias can happen if a dataset is built with the only photos provided by a specific media. Besides the dataset bias caused by the social and media biases, the biases can be also amplified in models. These two graphs show the relationship between dataset bias and model bias in two popular datasets. The x-axis represents the gender bias present in the dataset, and the y-axis represents the gender bias in the prediction result of the model trained with the biased dataset. As shown in the graph on the left, shopping and cooking were more biased towards female, and bias towards males was amplified for driving. In the graph on the right, spoons and forks produced biased result for women, and sports gear showed the result with an amplified bias for men. That is, the visual biases can result from the dataset bias caused by the social and media bias, and model bias can be created by amplifying the bias in the process of learning the biased dataset. So now we know where the visual biases originate from. Then what happens if applications use biased computer vision models or datasets? At the user level, it can impact the user's perception by reinforcing the user's prejudice towards biased results. For our society, it can create various social issues since biased results may discriminate against people in certain groups. Then how can we prevent such a harmful impact of visual biases? To prevent having biased results, we first need to understand what types of biases are there and mitigation strategies at the different levels. So I will introduce the three types of biases in computer vision. The first bias is accuracy disparity. This happens when the model's prediction accuracy differs across groups. For example, the model only works well for younger faces, but with poor accuracy on the older faces. So that is the accuracy disparity. And the second bias is spurious correlation. A spurious correlation refers to a connection between two variables that appears to be a causal, but the dependencies between these two variables are due to some unseen information. And the third bias is representation in the dataset. This happens when each group has an non-uniform sampling size. For example, if 80% of datasets are female and only 20% are male, then there is a representation bias. The accuracy disparity measures the performance gap between the groups of protected attributes, allowing us to evaluate the fairness of computer vision models. And the gender shade is one of the most representative papers that cannot be left out in the computer vision fairness. In this paper, the authors showed that the accuracy disparity across genders and skin tones in well-known commercial gender classifiers. More specifically, the authors measured the accuracy using the average faces of lighter females, lighter males, darker females, and darker males. The results showed that in all gender classifiers, the accuracy of darker females was significantly lower than that of other faces. In particular, the largest accuracy gap between darker females and the lighter males was 34%. A spurious correlation represents a connection between two variables that seems to be a causal relationship, but really is not. A causal relationship describes the cause and effect relationship between the two variables, where one variable directly affects the other. However, in a spurious correlation, a relationship between two variables is due to the third confounding factor that affects both variables. In the paper, Men Also Like Shopping, the authors found spurious correlation in computer vision models. For example, in a given image with a man in the kitchen, the model predicted the gender of a person in the image as a woman. We find here a spurious correlation between cooking and gender. In fact, there is no logical causal relationship between cooking and gender, but the reason for this result is an unbalanced data set. In the set of images with the label cooking in the dataset, there are far more images with women than images with men. Because of that, if a model sees a spatula or a kitchen as a background in the image, it may incorrectly determine the gender of the person in the image as a female. The paper, The Turning a Blind Eye, is another representative fairness literature that shows a spurious correlation. The authors analyzed the performance of the age classification model using IMDb, which is a dataset widely used in computer vision. However, in the dataset, they found a significant bias towards younger women and older men. This graph shows that there are more female images than male images in ages younger than the 30s. And on the other hand, there are many more male images than females in those in their 30s and the older. In this way, when a model is trained with unbalanced data, a spurious correlation may occur between age and gender, even though there is no causal relationship between these two variables. In other words, the biased model makes incorrect predictions as women are younger and men are older than their actual ages. And this figure shows the feature representations of age classification. However, the features are clearly separable by gender, even though it's an age classification, showing that the model has learned the gender bias in the dataset. The representation bias refers an unbalanced distribution between groups of the protected attributes in a dataset. In the fair face data, the paper, the authors evaluated the benchmark datasets widely used in the computer vision field. And this graph shows that except for the fair face dataset, all the other datasets are severely unbalanced across the race groups. In most datasets, more than half of the faces are white, and they are dominant over other races. And the problem is that the models trained on these unbalanced datasets only work well for the white faces and can produce the erroneous result on the images containing the face of other race groups. There's another recent work understanding and evaluating the racial bias in image captioning. The authors showed that the gender and race are ununiformly distributed in the COCO dataset. The authors found that there are twice as many males as there are females, and there are 7.5 times more lighter-skinned people than darker-skinned people in the COCO dataset. And they also found that there is a big difference in the objects and backgrounds in the images depending on the skin tones. For example, the lighter-skinned people tend to be pictured more with the indoor and furniture objects, while the darker-skinned people tend to be more with the outdoor, sports, and like vehicle objects. Again, the bias in the dataset can be learned by models, and that will eventually lead to biased predictions as a result. So far, we have talked about the origins and the types of biases in computer vision and their impacts on our society. And now I will introduce the types of bias mitigation strategies in computer vision. And there are 3 types of mitigation methods, including make a fairer data set and using synthetic data and algorithmic intervention. And I will go over each strategy and explain in more detail with like how the bias mitigation was achieved. The first strategy to mitigate bias is to build a more fairer data set. As we discussed the problem of the unbalanced data set, it is very important to have a data set where the data samples across the sensitive attributes are uniformly distributed. For the face image dataset, fair face is known as the first and the fairest dataset. The dataset has a balanced race composition of 7 race groups, including white, black, Indian, East Asian, Southeast Asian, Middle East, and the Latino, as well as the balanced gender composition of the male and female. And this balanced dataset helps the model can be, mitigate the bias. So the table shows the gender classification accuracy using the different face dataset. The result shows that the fairer dataset, the fair face, helps close the performance gaps over the different groups in race and gender. And the next mitigation strategy is utilizing the synthetic data. For example, the paper Gender Slopes uses the synthetic face images as shown in the figure. Using this method, the synthesized images that are more feminine or masculine than the original image can be easily generated. This approach can be used to make a balanced data set. For example, we can create more female images if a data set contains a larger number of males than females. On the other hand, the synthetic data can also be used for the validation purposes. In this paper, the authors generated more feminine and masculine images than the original images and used them to assess the commercial computer vision tools. Since the only face can be controlled in the synthesized images, it is possible to measure the fairness of the commercial tools. And lastly, we can use the algorithmic interventions to mitigate the biases. The adversarial learning is one of the methods of algorithmic intervention. The goal of adversarial learning is to prevent the model from learning protected attributes. And to achieve this goal, the regularization loss is often utilized. And this objective function is from the paper Turning a Blind Eye. Here, the LP represents the loss of the primary task, and LS indicates the loss of secondary tasks, which are related to the sensitive attribute. And finally, the confusion loss is added to induce the sensitive attribute not to affect the main task. And as shown in these figures, the feature representations were separable by gender in age classification task before the biasing. But however, after using the adversarial learning, the feature representations become invariant to gender. So I introduced some literature to help understand the biases in computer vision, and Angelina will continue the second part of the tutorial. Thank you.
Which of these two is it? Is it this button?
Yeah, you can share your contact window. Yes.
Okay, great, thank you. I will talk for about 20 minutes and we should have 15 minutes for questions at the end. So in this half of the talk, I'm going to discuss how we might apply computer vision in practice and the different fairness considerations we should keep in mind when we do this. So the running example I'm going to be using is a social scientist who wants to filter the contents of a very large corpus of archival photographs they have to study the representation of cars as a method of transportation. And computer vision would be useful here because there's just such a large corpus of photographs and they only want to look at the ones that are relevant to their task. So first, I'm going to talk about how you might get started with this. And so this involves thinking about whether this task is appropriate and also finding available tools. So first, computer vision, like other kinds of technologies and also machine learning, it's important to think about if it's actually appropriate for this kind of task. And so some examples, there's been one line of work that talks about the different harms of facial recognition technology. And this has been compared to plutonium because the type of regulation that is required for facial recognition is argued to be as severe as that for nuclear waste. And so one of the arguments here is that anything that assigns numbers to faces can kind of reify different kinds of categories such as race, which is a social construct, and also legitimizes the subordination of different groups of people. Another example is through the harms of gender recognition technology. And this can have a lot of harms, such as reifying that gender is a binary, and also that it is something that can be visually inferred from someone's face or physical appearance. This especially has unique harms for people that are different kinds of gender minorities, such as trans or non-binary people. And another more recent line of work has also looked at the harms of different kinds of emotion recognition and the nuances that this comes when you try to infer this about people. And so if we think about our example of a social scientist wanting to filter their corpus of images for cars, we might determine that computer vision is appropriate for this task because the presence of a car is a visually discernible characteristic from an image. In a lot of cases, though, computer vision may not be appropriate for the task, and then you would probably want to think about doing something else. But if computer vision is appropriate, then the first step can be to look for whether the model already exists online. And so there's a lot of different resources. One example is this website called Papers with Code. And like the title suggests, it contains a large repository of different papers with their associated codes and models. However, it might be unlikely that there exists a model online that is exactly suitable for the purpose that someone may want. And so here it's useful to use pre-trained models. And so pre-trained computer vision models can be fine-tuned for a specific task, but it's helpful to have a model that has already learned different kinds of important visual features. So for example, that edges and lines are things that are important in an image to be used. And so then when you fine-tune your own model, you don't need as many training examples. And so there are two main types of pre-trained models. The first is supervised learning. And supervised learning is when you train from a set of images that have associated labels. So one common supervised learning task is on ImageNet. And here you classify every image to be one of 1,000 different objects. There's also concerns here because the pre-trained model may encode different kinds of spurious features. So perhaps in this data set, if women are appearing in kitchens more than men, these could be encoded into the features that the model is using. The other type of common pre-training is unsupervised learning. And so here, there are no labels associated with images. And so random kinds of transformations are done to the images, and the model is just learning these kinds of meaningful visual features. And so regardless if you use a model directly out of the box or take a pre-trained model to apply fine-tuning on, it's important to understand the limitations of these models. And so model cards have been proposed as a kind of documentation to accompany different kinds of models. And these talk about how the model is trained, the kinds of use cases that are intended for, and also their limitations. And so once again, returning to our running example of wanting to filter this data set of photographs. For those with cars, we could decide that we want to use an object recognition model, which could do this task, and those are very common online. However, because our data set is specifically archival photographs, we might need to fine-tune the model on our data set so that works better. And so here, we could use an existing model, but we will further have to fine-tune it on our own data set. And so if the model doesn't exist, or the model doesn't exist exactly in a way we can use, then we'll have to look for a data set to fine-tune or completely train a model on. And so if there does not already exist one, then the next step is to collect your own data set. And this is a very hard task that I will not go into much in this talk, but just talk about how there's been a lot of calls about how this should become a more deliberative process that works on not extracting the data from people and different privacy concerns there. And so given at this point we either have some sort of model we can use or we have trained our own, the next steps are using existing methods in order to screen for biases in the data and the models. And so this is not an exhaustive set of concrete steps to follow. It's just kind of an example of how you might go through this and an example of the different fairness concerns to keep in mind when we are using computer vision. And so now I'm going to talk about the different existing methods we can use in order to screen for biases in data and models. So first, in terms of screening for biases in the data, there are different kinds of implications. The different kinds of under, over, or harmful representations can impact how a model performs in different kinds of settings. And this is important to understand so we know if we can preempt even training the model by collecting different images and annotations for our data set. There also exists a large number of existing tools and documentations that can assist this understanding of these very large-scale visual data sets. So the implications of this, so as one example, if we think about the ImageNet data set, which is a common pre-trained data set that people use, there's very low representation of images outside of the United States and Great Britain. And because of this, this can have different impacts on models that are trained on this. So for example, for common object recognition data sets, they found that it works much better on images from these countries that are represented. So in this figure, we can see that there's an image of soap from Nepal, and none of the common object recognition models are able to actually recognize it as soap. However, they are all able to recognize the soap pictured from the United Kingdom. And so this is just one example of how underrepresentation can lead to harmful impacts in a model. Other kinds of problems in data sets can be if there are inappropriate images and different kinds of denigrating slurs. And these can also be very harmful for models trained on it, and it might be caused to preemptively perform different things onto the data set before you actually train a model. And so just like it's unclear if different encoded features in the pre-trained data set or in the pre-trained model and biases there may propagate into the fine-tuned model, it's not always clear that any data sets that have biases will lead to biases in the model. However, it's still important to understand so you know what to kind of look out for. So one thing that can help is data sets for data sheets, and this is a type of documentation that has been proposed to accompany a data set. And the data sheets covers different things. So for example, how a data set was collected, different kinds of underrepresentation and limitations that come with it, as well as maybe intended use cases for models trained on this data set. And so for anyone collecting their own data set and planning to release it, it's also important to write up data sheets so that other people that will one day use your data set can know the limitations that come with it. There also exists a large number of existing tools you can use because these visual data sets now are on the order of magnitude of tens of thousands to even over 1 million images. It's very hard to attractively figure out what might be in it. And so Google has a tool called Know Your Data that works on TensorFlow image data sets and automatically surfaces different kinds of correlations in the data. And there's also a tool called Revise, which takes in as input an image data set and its annotations and will return different kinds of findings along the axes of object types, people attributes such as gender or race, and also geography. So going back again to our example of car recognition for social science, we may determine that cars and roads probably look different across different geographic regions. And so here, if we use a tool like Revise, we can kind of figure out what the geographic distribution is. And we can see that most of the images are in this particular data set are coming from North America, Western Europe, and Australia. And so if we do think that the cars and roads of the underrepresented regions look very different, we may want to collect more images for a data set before we actually train a model. Next, I'm going to talk about how we can use existing methods to find biases in models. And so here I'm going to talk about the interpretability of the model, and this allows us to find biases in the model's reasoning. Then I'm going to talk about evaluation for fairness, and this allows us to find biases in the model's output. And so for interpretability, there's a few different axes that we can think about the different methods and the different trade-offs that they come with. And so one is that interpretability can result in models that are interpretable by design, which means that they were explicitly trained and formatted in a way to be interpretable. We can also use post hoc methods. And so this means that we apply a method to an already existing model to try and understand why it made the decision that it did. We can also consider interpretability in terms of local explanations or global. And so local means that it will explain why one specific image was classified to have a car or not, whereas global explanations mean that you will understand why the model would classify what the model thinks are car-like features and cause it to classify cars at large. And so for choosing models that are interpretable by design, these can be very useful because the mechanism that it uses to classify a model is itself interpretable. However, the cost of this is that there's often going to be worse performance. For post hoc methods, these can result in higher accuracy, but the interpretation methods may not be entirely faithful to how the model actually reached its decision. Local explanations can be useful if you want to understand just one specific model decision. However, global explanations are more useful if you want to understand why an entire output class is used for a model. And so there's a large amount of work in this area, but I'm just going to talk about two of these works today. So the first one is called GradCam, and this is post hoc, which means that it applies to a already existing computer vision model, and local, which means that it explains one image and classification at a time. And so how GradCam works is that it produces these salient maps, which tell you what kinds of features are most impactful to the model's decision. So in the top image, we can see that when the model is classifying dog, it is looking at the top half of the image at where the dog is. And the red indicates where the model is looking and using to classify it. And in the bottom image, it's looking at the bottom half when it's classifying cat. And so as an example of how this can unveil fairness-related harms, prior work has found that for an image captioning model, when it produces the sentence, a man sitting at a desk with a laptop computer, when it generates the phrase a man, it's actually looking at the computer and not looking at the person at all. And so here, not only do we find that the gender classification itself is wrong, but also the reasoning is wrong because it's producing this gender stereotype by looking at the object. Although also this is a form of gender classification, which should not necessarily be condoned. Next, I'm going to talk about TCAV, and this stands for Towards Concept Activation Vectors. And this is post hoc, which again means that it's performed on an already existing computer vision model, but now it is global. So rather than explaining just why one image was classified as such, it will explain why an entire class is. And so in this example, the concept that we're trying to understand is stripes, and the class label is 0. So the question is, how important are stripes for this classifier to recognize something to be a zebra? And here it uses the directional derivative of this concept of stripes to understand the impact it has on the zebra-ness classification. And using TCAV, one can probe a model to understand why it is classifying certain kinds of groups. So here, in this example, using TCAV to understand why a model is classifying ping pong ball in an image, we see that the concept of East Asian is actually very explainable for why this model is classifying this. And this can be problematic if we don't want to encourage this kind of spurious correlation. So once again, going back to our example of car recognition for social science, we may wonder whether, so we may have a belief that the color of a car is correlated with some kind of demographic group. And if that's the case, then we would want to understand the influence of color on car classification. We might also want to understand whether our detection model is able to recognize cars when they're pictured from a bird's eye view. And here it appears as if cars don't have wheels. And so because this is post hoc, we want to understand this on a model that already exists, as well as global, we can use TCAV. And so using TCAV, we can understand the influence of both color and wheels on car classification. Finally, I'm going to talk about evaluation and the existing technical methods we can use. And so, as Seungbae had also talked about earlier, one common method is looking at different accuracies. And so in this work, they had found that there is, on the task of gender classification, there's much different accuracies for people that were lighter and male rather than people who were darker and female. In another line of work, they look at the different output distributions. And so here they took very uniformly posed people, posed men and women from professional photos of US politicians and fed them through different image tagging systems and compared the outputs of the tags. And because the people were posed similarly, one would probably expect that the tags also be similar. However, instead, they found that the top labels outputted for men were words like official, business person, and spokesperson, while those for the women politicians were smile, chin, and hairstyle. Another type of evaluation also that Seungbae discussed earlier is bias amplification. And so in this work, they found that different kinds of correlations that were in the training data set, so for example, women and cooking, which were in the training data at 33%, is actually amplified by the model at test time to be 68%. And so while the prior kinds of evaluation could be attributed to different biases in the data, this is solely attributed to the biases that the model is amplifying on top of what already exists in the data set. However, in our later work, we found that this prior work made a number of different assumptions in the measure of bias amplification. So for example, the metric that they use assumes that every group is already represented equally in the data set, and also is only able to measure negative correlations, such as that women may not appear much with technology-oriented objects, only in the case of binary attributes. So in our work, we propose a new metric that does not make these kinds of assumptions. And this also tells us that when we're measuring fairness, there's a lot of important considerations to think about, and different kinds of technical choices we might make in our metric that seem harmless at the time may have different kinds of normative implications. And so in a line of work in natural language processing, but is also mirrored in computer vision, they discuss how the word bias is frequently underspecified in fairness measurement, and it is often not even connected to a real harm. So it's used to refer to a whole host of different things, but it's important to actually connect what this bias is to why it is harmful to different groups of people. And so even disaggregated analyses, such as comparing accuracy across different groups, should involve very careful consideration. So for example, what is the data set that we're even measuring this accuracy on, and whether accuracy is the performance metric we should compare or other kinds of metrics. Another line of work has said that thinking about fairness without thinking about the context that this technology will actually be situated in is kind of nonsensical. And so if we try to understand a facial recognition system and its fairness without thinking about how that facial recognition system will actually be used in practice, we can't even think about the different fairness implications there. And so thinking about this context will help us kind of address what kind of bias matters here and how it's connected to the harm. And zooming out a level, another line of work has talked about how fairness itself is even a very contested construct. And so for each time we're trying to measure it, we should really articulate what is the notion of fairness we're thinking about and why it is relevant for this particular task. And so going back one last time to our example of car recognition for social science, we may know that cars of different prices probably look different. And so false negatives here might be the metric that is very important, because If in our data set we're unable to recognize the images that have cars that are not worth as much, then our data set would be very biased. And so here in this data set, even if we happen to have the labels for gender of the owners of each car, if we had information that said that gender does not impact what a car looks like, that might not even be a relevant fairness metric to look at here. And so the task at hand will kind of dictate what kinds of fairness matters for each case. Okay, so to summarize, Seungbae in the first half talked about understanding biases in computer vision. He talked about understanding the origin and impacts of computer vision biases in media and society, and also reviewed different types of dataset bias, model bias, and bias mitigation strategies. And then in the second half, I talked about applying computer vision with different fairness considerations to keep in mind. And so here I talked about getting started and first thinking about whether this task is even appropriate for computer vision or technology, and also finding available tools. And then using different kinds of existing methods to screen for biases in the data and models. And so our goal here in this tutorial was to introduce some recent ideas in computer vision fairness and also provide different pointers to the literature. And now we have some time for questions. Okay, yeah. Anyone can just raise their hand. Yeah.
Hi, really nice talk. I love it. It's my field of research. So my question is on the use of synthetic images to mitigate fairness problems. Like in gender slopes, aren't we adding bias when we are creating male or female faces? Or even if we talk about skin color too. Aren't we adding more bias in the data set?
Yeah, I have one answer and probably other people have different answers, but to start off with, I completely agree. And I think that synthetic examples are commonly used in different kinds of machine learning for data imbalance. But I think specifically for facial images, I think my opinion is that they should not be used because of these problems. I think that they reify what masculine and feminine faces look like. And I also think that manipulating faces for especially skin tone has very harmful historical parallels. And so that's kind of my stance on this, but I'll let the other speakers speak too if there's other opinions.
Yeah, so I'm happy to chime in. So basically, fully support that with one small caveat. I think there are cases where it's used kind of the same way that an internal representation of a model is used. So I think as long as you're not, as long as you're sort of using it for the kind of as an internal representation of the model, and you're evaluating the model on sort of what is it learning downstream, and you're not actually showing these images, right? So I would argue that the true harm would come from showing the images or from the downstream behavior of the model. And so if you can sort of avoid that, then it's kind of part of the internal process of the system. So that's the one small caveat there.
So I think I can also add to that, answers. I think I agree that it could be problematic to synthesize or generate concepts like gender or race, which are complex and could be very subjective because the nature of this whole subject, supervised learning requires human labels. But I think in the limited application, we could still take advantage of those synthetic images. So for example, if we narrow down the dimension of variance, such as skin tone or the color of these pixels, and then try to, for example, tell the models, do not use skin tone as important features for the given task. And then we could use synthetic images in that kind of scenarios. So instead of trying to learn the holistic concept purely from the synthetic data, we could still try to find out how we could use limited information and signals that we can find from these synthetic images.
Thank you for a great tutorial. My question is about using tools like TCAD, and maybe in your specific example of the card recognition for social science. How would you go about deciding what sort of input images to use when you want to understand things like, is it basing its decisions on wheels or color? Because if you're using natural images, I suppose it's hard to know whether there's already kind of correlation and bias in the examples that you've chosen, right? So would you use natural data or synthetic data for tools like TCAD?
Yeah, I'm not an expert on TCAD, but I think I imagine that natural images would fit the real distribution of images better. And so there, I think as long as you find like a diverse set of images that represent wheels or tires, such that there is not like a strong spurious correlation in the background, such as the tires all happen to be on this specific type of grass and it might be confused there, then you could kind of get around that.
Yeah, I'm happy to quickly chime in there. Yeah, so you're completely right. For these interpretability methods, the use of data set that you're using to try to interpret the model has a profound effect. And that's actually a very important and I think under-specified point in interpretability. And we actually have a paper under review right now that sort of makes this point very explicit, sort of how much the actual data set has an impact. And so I think in terms of which one you would select, so generally you're doing interpretability to figure out how well your model does on your particular task, or sort of how will it make decisions in your particular setting. And so hopefully you have some data that's sort of representative of what your downstream setting is, and that's what you would use then to do the interpretability. But yes, the interpretability methods tend to be subjective to the particular data set and setting and are not objective with respect to the model.
Thank you for your great conversation. And I have two questions. The first one is there any specific way to measure any bias in the model? And the second one is, if there is a bias in the model or any bias in data set, what if we suppose we have some bias in skin tone, and then is there any specific way to remove the skin tone in the data set, or diverse the skin tone, like with the same image and make a synthetic data set with different skin tone? So is there any way to deal with this problem?
Yeah, so for your first question, it was on measuring biases in models, right? I think going back to what I mentioned about the word bias being very underspecified most of the time, I think it would depend entirely on the downstream task and what would constitute bias and harm there, and the types of measurements you could perform. And so some of the examples include like accuracy differences, difference in output distributions, bias amplification, but I think it would really depend on the task. And then for the second question, I think that was similar to what was asked earlier about generating synthetic examples to help for data imbalance. And so as Olga had mentioned, especially for facial images, they probably should not ever be made visible to people. But it's possible that just like in terms of the internal representation of the model, it can use these different kinds of manipulations in the model and like to augment a type of underrepresented data.
I think my question was also on a similar vein. In terms of being able to measure the bias that's present in your model, I was wondering what the maybe benefits or downsides are of including these labels or additional metadata about participants in your data set. So if you include extra contextual information, say about their race, does that allow the model to correct for bias in some way? Because it's clearly already learning these underlying biases without being provided the actual labels for it. So is there any benefit there?
Yeah, definitely. I think so. I think that one of the earlier lines of fairness work was kind of fairness through blindness, and there you use different kinds of adversarial methods to try and erase like race and gender. But that feels very unrealistic, and it feels kind of like when people describe that they don't see race, right? And that is not the right solution to racism. It's rather just like, so now there's a new thought through like fairness through awareness, where you should be aware because these differences are there and they exist, and only by being aware of them can you kind of correct for them and these different kinds of things, because you just cannot remove it. They're like prevalent in all sorts of different kinds of correlations.
Thank you for the great tutorial. So my question would be a little bit more philosophical. So can a model be biased, or is it always the data that the model is trained on?
I think both. I think all data is biased, all models are biased, I guess. But models can be biased in a different sense if you are trying to think about things that aren't directly applying from the data set bias. So model bias amplification is one example where it will further it. And also I think models that even might be fair with respect to different kinds of data bias can be used in unfair ways. So I guess like facial recognition, if the use case is for over surveilling communities of color, that is kind of unfair in the model and might be unrelated to the data because it might work equally well for all groups of people.
Sorry, I just want to ask to that answer actually. But there are training methods that can amplify bias, or like if you do early stopping, for example, Sarah Cooper on that. If you do early stopping, then basically it's going to learn the easiest example first and the more difficult examples last. And so if that's related to how bias is present in your data, then your model might just be unfair just because you have stopped at the first one.
Kind of on that note, are there other training strategies that have been shown to kind of mitigate that bias, like something like curriculum learning used in that context, because then kind of giving it a more mixed set of labels that it can learn from. So you're mixing up the classes rather than it learning the easiest first, it's able to learn a better distribution of difficulty. Would that be useful? I don't know if there's any work that's coming down on that.
I can't hear super well. I'm sorry, I can't hear the discussion super well. I would be happy to chime in. But
yeah, I think the question was if there's different kinds of like learning methods that might help a model not amplify bias as much. So examples were like curriculum learning and like early stopping and these kinds of things.
Oh, yeah, absolutely. So early stopping is basically regularization, right? And regularization certainly helps prevent, overfitting to particular groups or particular patterns, right? Is sort of can help in kind of long tail training settings, and early stopping is basically an example of regularization. So it can help. I think there's a lot of machine learning literature on how to do kind of bias mitigation, and there's an awesome book online, right? Fairness in Machine Learning by Seungbae and Moritz Hart and Arvind Narayan, and that's freely available, and that does a very deep dive into like kind of the different algorithmic strategies for bias mitigation models.
I think one thing I'll add is that for these kinds of like automated strategies and regularization, it's very like there's no really technical difference between a spurious correlation and an actual true correlation of the thing, and it's not always clear which one will be more salient. And a lot of these methods will work just by learning the more salient one first or the less salient one first, but it really requires a human to kind of say which are the permitted correlations to have and which are the inappropriate ones.
So we also have a couple of questions in virtual from the virtual participants. I don't know if you want to read those or tackle those.
Yeah.
Yeah, so I can try to read the first. So when we diversify data collection to improve its representativeness, how can ideas from crowdsourcing support this idea? And also models trained with better representative data sets could potentially help better off-the-shelf pre-trained recognition models for use in, let's say, self-driving cars. So, I mean, I can take a stab at this. I don't know. Oh, you want to go ahead?
No, you can answer. Yeah.
I don't know. Go for it. Go for it.
Should I just so yeah, the right. So
I mean, we use all kinds of the labeling services, and then the workers, and then we don't many times we don't even know who they are, and then where they are located, and then by asking them to label our data, and then our data itself, the raw data, image and video data, we don't always know the sources and the types or the content or the styles in the data set. And then we're kind of adding additional layer of human biases, and then oftentimes that is seen as an interpretation of a biases, especially a task is a subjective task such as emotion recognition. And that is kind of more subjective than object detection, where the task is to classify the type of object, and then we may expect a little bit less amount of biases. But the point is, well, there are some underlying biases in terms of the data composition in the first place, in a way that we collect the raw images, and then on top of that we have this additional layer of biases. And then the one thing that we can try to do is, of course, try to have a more diverse set of participants and laborers and workers. So instead of using kind of one particular country as the source of workers, we can try to incorporate the more diverse set of laborers from multiple countries, and then they may have different cultural values and expectations and understanding. So that could be one way to kind of diversify the internal diversity in the label set, and then that's one way. And then another thing that we can think about this is, well, the bias in terms of statistical bias is one thing, but I think the more important issue is there are kind of fundamental questions about whether it is even ethical to do certain kinds of things, like even facial recognition, depending on the application, and then the audience, it may be problematic. And then I think that's another area where we can use kind of more diverse set of ideas, meaning we could kind of get help from the more diverse audience, so that they can review those technology, and then the assets that we have, the data sets, and then the models, and then the application, so that we can try to prevent from having kind of more difficult or ethical issues happening. Do you want to add? I don't know whether actually that answers your question. Olga, do you want to add more?
No, I mean, I think you said all the right things. I mean, yes, absolutely, we can leverage ideas from. The short answer is absolutely we can leverage ideas from crowdsourcing and should to support this. Yes, the one last question, just in the interest of time. So I think, Angelina, this is probably for you, but interpretability research is for explaining how and why the models make the results. However, interpretability in computer vision, like GraphCam, which is cool, but it looks too obvious to humans without explanation already. So we can see why a cat is a cat in the image. Can you explain other cases where humans need an explanation in the vision model?
Yeah, I guess for like classification, that is a more simple example, but for the different kinds of things, such as image captioning, where it produces this whole sentence, and you want to know for each part of the sentence, what parts of the image are influencing it, maybe why it pointed out certain parts of the image is important to mention and remark upon in this one sentence caption and not others, it can become more complex to understand. And yeah, I think we're also out of time because it's lunchtime. So that's it for. Thank you, everybody.
Thank you very much.
Well, thanks, everyone. Thanks, Angelina, for representing us in person.
Oh yeah, thank you.
Enjoy your lunch.
Enjoy CVPR in New Orleans. Cool.
Right, you should close it.
You can go on.
Drop off.
Yeah,
Bye.
bye. Yeah. Bye.
Hello.